Hello scholars, today we're going to do skill 12 lesson analyzing exponential functions. So let's go over it together. There are a lot of laws, right? But one of the laws, it's called Moore's law, state that processor speeds or overall processing power for computers will double about every 18 months. Likewise, the cost to produce the comparable computer will be cut in half. So what does that mean? To simplify the mathematics, let's assume, I know the Moore's law says 18 months, but to make our life easy, we're just going to assume it's going to take 2 years and see what the processing power will be over the years and then what the cost will be over the years as well. So example 1, in 1988, number of transistor in the Intel 386, it sounds like foreign language to me, which is foreign, English is foreign language, was 275,000. What was the approximate transistor count of the Pentium 2 Intel microprocessor in 1998? So let's look at it. We say it's going to double every 2 years, so that's what we're going to assume. So let's just go ahead and then double that. So 0, 0, 0, 0, 5, 1. So it's going to be 550,000. And I'm going to pause this and fill it out and come back. Okay, I thought it was going to be complicated math, but it wasn't really. So it double every 2 years. So I just plug it in. Now we're going to go ahead and plot those points together. So 1988 is, so these are the X value, the years, and the transistor count is the Y value. So the first, when it was 1988, it was 275,000. So it's like really low over here. 990, 550, so somewhere in the middle. 92, it's over 1 million. 94, 2.2 million. 96, 4.4 million. And 98, 8 point something million. So it looks like that. So when you connect your points, notice it's not going to be a linear. It's going to be more of a bent shape. And actually, we call this the exponential function because every year it's increased by double. So you're raising to the, it's going to be 2 to the x power. So as x increase, you're doubling it more and more. This is called the exponential growth. Why is this called a growth? Because it's literally just growing. It's going up exponentially, getting bigger. Likewise, let's do the same thing. On the problem, it says the cost is gonna get half every 2 years. So we're gonna cut this in half. So divided by 2. 1,500, cut this in half. 750, cut that in half. 375, cut that in half. Oh, look at this. 187.5, cut that in half. 93.75, cut that in half. You get $46.87. Wow, that got really, really cheap. That is crazy. Okay, so let's go ahead and plot those points. 2002, cost was 3,000. 1,500, 750, 375, 187, 93. Oh, it's getting really, really closer. So it looks like this. Notice as x gets bigger, your y gets smaller. So it's going to be exponential decay, and it's going to have a formula of something, half to the x power because it gets half every year. Unlike on the top one, it double. It's a half. Alright, so exponential function has a form of the following. A times b to the x power. Notice your x is in the exponent. That's why it's called the exponential function. Duh, right? Alright, so the b, it's going to be the base. That's an easy way you can think about it, right? The base of the exponent. That's how we learn it. It's also called the growth and decay factor. You're going to learn in the next page, depending on the b value, your graph will look a lot different. So we can have two different cases when the base is greater than 1 or when base is between 0 and 1. Notice your base cannot be equal to 0. Equal to 0 nor negative. So it has to be positive, but it has to be either between 0 and 1 or greater than 1. A is the initial value, and A cannot be equal to 0. So these conditions, I mean, I feel like when I learned this in high school, I kind of ignored it. But as I learned this more in college, like those are very important for me to recognize it. So that's the exponential function. Now, let's look at what's happening. I'm going to zoom in a little bit so you can see it better. All right, exponential growth function. When the b value, what was the b? Let me write down. It was y is equal to a times b to the x power. So b was the base. When base is greater than 1, then the graph will grow away from the asymptote as you move left to right. Okay, so I mean, it makes sense, right? If base is greater than 1, so I'll just give you an example. Y is equal to, I don't know, whatever, 2 times 3 to the x power. Your base is 3. So as x gets bigger, you're like multiplying 3 and 3 and 3 and 3 and more. So it's going to get really, 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 really big. Does that make sense? All right. So when there's no shifting whatsoever, the x-axis, y is equal to 0, is an asymptote of the graph. Particularly, it's going to be the horizontal asymptote. So the exponential function has the horizontal asymptote. Asymptote is an imaginary line that the graph gets closer, but never touches it. Got it? So regular exponential function, it has a horizontal asymptote at y is equal to 0. Usually for the exponential function, your domain, the x value is going to be negative infinity to positive infinity, as you can see. But the range, I mean, this line, your graph is going to get never closer to. So do you guys notice that it's going to have all the positive y values? In other words, y is going to be greater than 0. All right, when your base is greater than 1, that's also other possibility. What if I say y is equal to negative 2 times 3 to the x power? What would that look like? What's going to happen here is, I mean, you can kind of apply what we learned in the first quarter. Notice there's no negative and there's a negative in the front. So when the negative is in the front, that means y changed the sign. So do you guys remember that means it's going to be x-axis reflection? Yeah. So you're going to take this, reflect it over the x-axis. So it's going to look like this. It's going to look like that. So when the base is b is greater than 1, you can have two possibilities. If the a value is positive, it goes up. If a value is negative, it's going to be reflected over the x-axis and goes down like that. And this is going to be called the decay. Why is this called the decay? Because as you go to the right, your y goes down. Whereas this one, as you go to the right, your y goes up. So that's a growth, that's a decay. Growth, decay. Growth, decay. Got it? All right, now let's look at when your base is between 0 and 1. When your base is between 0 and 1. So let me give you an example. Y is equal to 2 times, I don't know, 1/3 to the x power. I'm just making it up. So your base is between 0 and 1. As x gets bigger, like what's going to happen if you multiply 1/3 and 1/3 and 1/3 and 1/3 and 1/3 and 1/3 and more? Do you notice that your y value is going to get smaller? Yeah, so your y value is going to get smaller, smaller, smaller. That looks like this. The domain of this function is going to be, again, it's an exponential function, so negative infinity to positive infinity. Range is going to be y is greater than 0 because it's up here. What do you think is going to be the asymptote for this function? It's going to have a horizontal asymptote. Where? Right here at y is equal to 0, just like the top one. It has the same horizontal asymptote going on there. Okay. What else is possible? I'm going to give you an example. Y is equal to negative 2 times 1/3 to the x power. So comparing these two together, do you see that negative is in the front? That means I'm going to take this function, reflect it over the x-axis, boop, boop. So it's going to come to the bottom. Looks like this. So that is possible as well. Oh, what am I doing? I drew it wrong. Sorry. It's going to look like this. There you go. There we go. And that's going to be, as I go to the right, it's getting closer to the x-axis, so it'll be growth. Because it is going up, right? That's increasing. So when I ask you to determine growth and decay, you look at what happened as you go to the right. Cool? Alright, so example on the right, I want you to determine whether it's a growth or decay or neither of them. Let's do the easy one first, graph first, right? What happened here? Boop. It's going down, so decay. What about this? Boop. Going up, growth. What about that? Going down, decay. What about that? Going up, growth. What about that? Going up, growth. So are we good for the graph? That one's the easy one. The function, equation of the function will be the hardest one. But not really. Just think about it. All right, so when I look at it, here's how you should do it. And this is going to be one of the examples you need to do after you look at this video. You first determine the base. Okay, so what is my base here? 2. This example right here, 2. When the base is greater than 1. Okay, so base is greater than 1. So I'm going to, okay, I know it's going to look like this. Boop, like that. It's going to be exponential growth. Now you look at the a value. What is the a value? The number that's multiplying the front. It's the half. So is it positive or negative? Positive. So will there any be reflection going on? Nope. So your graph is going to look just like that. So just by looking at that graph, what would that be? The growth. Okay, let's do a free move practice over here. Look at this one. 2 times half to the x power. What is your base? Half. Okay, so as x gets bigger, it's going to get smaller. So it's going to be exponential decay to begin with. That looks like this. And now you look at the a value. A value is 2. Is that positive or negative? Positive. So do we do any reflection? No, we don't. So it's gonna look like that. Is it growth or decay? Decay. I'll keep doing a few more with you. Look at this one. Y is equal to negative 2 to the negative x power. This one might be a little confusing to some of you. I will rewrite it for you. It's actually negative 1 times 2 to the negative x power. Because the negative 1 is being multiplied, so I just pull it out to make it look more easier. All right, what is your base? 2. So base is greater than 1, so it's going to be exponential growth to begin with. Boop, boop, boop. That looks like this. But now, notice, a value is negative 1. So what does that mean? That means there's going to be excessive reflection. So you're going to take this, boop, reflect it over the x-axis. There is my graph right here. The purple one. So now I'm looking at the purple one. Is that growth or decay? Decay. Oop, did I really use all my pen? Sad day. Yes, that is decay. So next, this one. What is my base? 7 over 10. So that's going to be what? Less than 0. So I'm going to start with the exponential decay. That looks like this. Alright, this one is a lot. And then, look what happened. A value, is that positive or negative? 0.4 is positive, so I don't have any reflection. However, do you see negative in front of the x? Oh yeah, yes. So what does that mean? That means your x changed the sign, so there's going to be y-axis reflection. So you take this graph, reflect it over the y-axis, boop, it's going to look like this in a pink color, therefore it'll be growth. I just showed you something different, right? So you not only have to watch for the x-axis reflection, you also have to watch for the y-axis reflection. Cool? Alright, last but not least. Ooh, what is happening here? Did it get printed wrong? Guys, is this the exponential function or no? No. What kind of function is this? It's the quadratic function, x squared. So x is not in the exponent, so it's neither of them. I can't determine exponential growth or decay because that's going to look just like a parabola. That was tricky, wasn't it? Alright, so now I need you to stop the video. Well, it's over. It's going to be ending, and do the next few examples on the delta mat, and then come back.